Hey everyone, and welcome. Today we're going to pull back the curtain on something called artificial neural networks, or ANNs, and we're going to do it by telling a story. A story of how scientists looked at the most complicated thing in the entire universe, yep, the human brain, and said, hey, could we build a machine that can actually learn?
Now, our whole philosophy here is that anyone can get this. Seriously. And to prove it, we're not going to start with a bunch of scary code or complicated algorithms. No, we're going straight to the original blueprint.
So, where do we kick things off? Well, forget about silicon and software for just a second. Our story actually starts with something way more organic.
The human brain. I mean, think about it. This thing is the ultimate learning machine, right? And for decades, that's been the dream, to build a digital version of that.
Okay, so just how powerful are we talking? Get this, your brain processes about 11 million bits of information every single second. And most of that is happening without you even knowing it. That insane level of power, well, that became the gold standard. The thing computer scientists were desperate to replicate.
So all of this led to one huge fundamental question. It's the same one that a young woman in our story, Yu, was asking herself. Could we actually build a machine that learns the way a brain does? Well, today we're going to find out.
All right, so if we want to understand the artificial, we've got to start with the biological. I mean, how do you even begin to copy something that complex? Well, you do what any good engineer does. You start small. You start with just one single tiny building block.
And that building block is the neuron. So on the left, you see the real deal, a biological neuron. It has these little branches called dendrites that slurp up signals, and then this long tail, the axon, that sends a new signal out. Now look to the right. That's our digital twin. Instead of dendrites, you've got inputs. Instead of the main cell body, you've got a node. And instead of an axon, you have an output. It's basically a simplified, math-based mirror of the real thing.
Okay, so let's zoom in a little closer on that artificial neuron. How does it actually, think or make a decision? Well, the cool thing is, it's actually a pretty straightforward, logical process. It's just a few simple steps.
So here's how it works, step by step. First, it gathers up some data. These are its inputs. Step 2, it applies weights to each of those inputs. Think of this like judging how important each piece of information is. You might trust a recommendation from your best friend way more than a random ad you see online. That's kind of what weights do. Third, it adds something called a bias, which is sort of like a thumb on the scale, making the neuron either more or less likely to fire off a signal. And finally, the activation function makes the final call. Do I send a signal or do I stay quiet? That's it. It's like a tiny little flowchart for making one single decision.
Okay, that makes sense. A single neuron makes a single, tiny decision. But so what? This is exactly where Yu, our character, got stuck. She was like, great, but how does a whole network of these things actually learn anything? And to answer that, well, we need to take a quick trip back in time.
You see, this whole thing didn't happen overnight. It evolved in a few key stages. Way back in 1943, we had the Threshold Logic Unit, or TLU. Honestly, it was just a fancy on-off switch. Then in the 50s, things got more interesting with the perceptron. This was a big deal because it could actually learn by tweaking its own settings. But the real revolution, the moment everything changed, was in the 1980s with the invention of backpropagation. This was the magic ingredient that finally let huge networks of neurons learn really complex stuff altogether.
So, what was the big leap between that early TLU and the perceptron? Well, here's the key difference. The TLU was totally rigid. Its rules were set in stone. The perceptron, on the other hand, was flexible. It could learn from its mistakes by adjusting its internal weights. It's really the difference between a simple calculator that just follows orders and a student who actually learns from getting things wrong.
But there was a huge problem, a critical flaw. The early perceptron could only solve really simple problems, ones that you could literally separate with a single straight line. But the real world, it's messy, it's complicated, it's almost never that simple. And for a while, this one limitation almost killed the entire field of AI research. It was a dead end.
And this is where backpropagation saved the day. I'm not exaggerating when I say this algorithm was a total game changer. Here's how it works. It lets a deep network learn from its own mistakes. It looks at the final answer, sees how wrong it is, and then sends that error message backwards through the entire network. It tells every single neuron, hey, you need to adjust your settings just a little bit so we get closer to the right answer next time. This was the key that finally unlocked the massive potential of these networks. So that brings up the question, how do these networks handle all that real-world messiness and complexity? Well, the secret is hidden in that activation function we talked about earlier, the little gatekeeper that decides if a neuron fires. And it turns out there isn't just one kind. There's a whole toolbox of them.
Yeah, seriously. Think of this like a toolbox for an AI engineer. You've got to pick the right tool for the job. Are you building something that just needs a simple yes or no answer? Grab the sigmoid function. Are you building out those deep, internal, hidden layers of the network? ReLU is your go-to. It's super fast and efficient. Or what if you need to pick one winner out of a bunch of different options, like figuring out if a picture is a cat, a dog, or a bird? For that, you use softmax. Each one of these functions gives the network a different superpower for tackling complexity.
Okay, so at this point, these networks are sounding pretty incredible, right? And they are, but they're not magic. And trying to train one means you're going to run into some really common, really tricky problems. There's a very good reason people call these things a black box.
Yeah, pretty much everyone who works with these runs into three big headaches. The first one is called overfitting. This is basically when the model crams for a test. It memorizes the training examples perfectly, but then when you give it a new problem it's never seen before, it completely fails. The second is the vanishing gradient. In really, really deep networks, that learning signal that gets sent backwards can get weaker and weaker until it just disappears. Learning just grinds to a halt. And finally, there's interpretability. This is the black box problem. The network might give you the right answer, but you have no idea why, and that can be a really big issue. Okay, so enough with the theory. How does any of this stuff actually apply in the real world? Well, let's circle back to our character, Yu, and her garden. She had a passion project, growing the perfect tomatoes. And she started to wonder, could this crazy AI tech actually help me get a better harvest? See, if she used a simple old-school model like linear regression, it would assume a simple straight-line relationship. Like, more sun always means more tomatoes. But any gardener knows that's not true, right? A reality is way more complex. An artificial neural network, on the other hand, can learn that non-linear truth. It can figure out that there's an optimal amount of sun and that too much is just as bad as too little. In other words, it learns the perfect curve, not just a simple straight line. And by the end of her journey, Yu came up with this really perfect way of thinking about it. She said ANNs are like a big maze of roads. When information comes in, it travels through the maze. Each neuron decides whether the information should be sent on or not based on how important it is. I just love that. It's such a simple and beautiful way to visualize what's happening inside. So when you boil it all down, that's what these things are. Artificial neural networks are an incredibly powerful tool inspired by our own brains that are amazing at finding hidden patterns in messy, complex data. So now that you've seen how the magic trick works, it kind of makes you wonder, right? If you had one of these, what complex problem would you teach it to solve?